Sequences, Part 1. What is a sequence? A sequence is an infinite ordered list of numbers, A1, A2, A3, A4, and so on. Notice the use of a subscript to indicate the ordering of the sequence. Brace notation is often used, as in A sub n, as n goes from 1 to infinity, or simply A sub n in braces. Examples. The sequence 1, 1/2, 1/3, 1/4 may be expressed as 1 over n as n goes from 1 to infinity. The terms of the sequence -1 to the n minus 1 divided by n squared as n goes from 1 to infinity are 1, -1 over 4, 1 over 9, -1 over 16, and so on. The terms 1/2, 1/6, 1/12, 1/20, 1/30, and so on are of the sequence 1 over n times n plus 1 as n goes from 1 to infinity. Notice the first term is 1 over 1 times 2, the second term is 1 over 2 times 3, the third term is 1 over 3 times 4, and so forth. Often it is convenient to use 0 as the starting index, in which case the sequence may be listed as A0, A1, A2, A3, and so on. For example, the terms of the sequence -1 to the n divided by 2 to the n as n goes from 0 to infinity are 1, -1/2, 1/4, -1/8, 1/16, and so on. The terms of the factorial sequence n factorial as n goes from 0 to infinity are 0 factorial, which is 1, 1 factorial, which is 1 times 1, 2 factorial, which is 2 times 1, 3 factorial, which is 3 times 2 times 1, 4 factorial, which is 4 times 3 times 2 times 1, and so on. These products are 1, 1, 2, 6, 24, 120, 720, and so on. Notice that the sequence here grows very quickly as n increases. We often describe a sequence by simply specifying the nth term. For example, A sub n equal to n over 2 to the n for n equal to 1, 2, 3, and so on describes the sequence 1/2, 2/4, 3/8, 4/16, 5/32, and so on. The formula for the nth term is affected by the choice of starting index. For instance, the sequence 0, 1/3, 2/4, 3/5, 4/6, and so on may be expressed as n minus 1 over n plus 1 as n goes from 1 to infinity. On the other hand, we could start with n equal to 0 and express the sequence as n over n plus 2 as n goes from 0 to infinity. It isn't necessary that there be a formula for the nth term. For example, the prime numbers are a sequence 2, 3, 5, 7, 11, 13, 17, and so on. The index is a dummy variable. Any letter can be used, although we normally use one of the letters I, J, K, L, M, or N. For instance, the sequence I times 3 to the minus I as I goes from 1 to infinity is exactly the same sequence as k times 3 to the minus k as k goes from 1 to infinity, or the sequence n times 3 to the minus n as n goes from 1 to infinity. The graph of a sequence. The graph of a sequence A1, A2, A3, A4, and so on is the set of points 1, A1, 2, A2, 3, A3, and so forth. Example. Let's consider the sequence n squared plus 5 divided by n squared plus 5n as n goes from 1 to infinity. The first few terms here are 6 over 6, which is 1, then 9 over 14, 14 over 24, which is 7/12, 21 over 36, which is also 7/12, and so on. Here's a graph showing the first 25 points on the graph of the sequence. Notice that all of these points lie on the graph of the function f of x equals x squared plus 5 over x squared plus 5x. In fact, the graph of the sequence consists precisely of the points on the graph of f whose x-coordinates are positive integers. The limit of a sequence. Let's look at an example. Let's consider the same example as before, the sequence n squared plus 5 divided by n squared plus 5n as n goes from 1 to infinity. Here's the graph of the first 25 terms of the sequence. This shows the first 50 terms of the sequence. Here's the first 100 terms of the sequence. And here's the first 200 terms of the sequence. Notice that it becomes clear that the points on the graph are approaching a sort of horizontal asymptote. Here, that asymptote happens to be the line y equals 1. Now, this is exactly the same horizontal asymptote that is approached by the graph of x squared plus 5 over x squared plus 5x. Consequently, the limit as n goes to infinity of n squared plus 5 over n squared plus 5n is going to be the same as the limit as x goes to infinity of x squared plus 5 over x squared plus 5x. We have computed such limits before. Since the degree of the numerator and denominator are the same, this limit is going to be the ratio of the leading coefficients, which is 1 over 1, or 1. This computation is an instance of a general fact which we state as follows. Suppose that a sub n is equal to f of n, where f is a function defined for x greater than or equal to 1. If the limit as x goes to infinity of f of x is equal to L, then the limit as n goes to infinity of a sub n is also equal to L. Another example. Consider the sequence n minus 3 times minus 1 to the nth power divided by n plus 2 as n goes from 1 to infinity. Notice that when n is odd, the numerator is n plus 3, and when n is even, the numerator is n minus 3. Here's a graph of the first 25 terms. To emphasize the behavior here, let's join successive points with straight lines. Here's the graph of the first 50 terms, the first 100 terms, and here's the graph of the first 200 terms. Notice that in spite of the oscillatory behavior of the sequence, points on the graph do appear to be getting closer and closer to a horizontal line, which here again is the line y equals 1. Because of the minus 1 to the n in the numerator, we'll justify our claim that the limit as n goes to infinity of this sequence equals 1 in a different way. Since the numerator is always either n minus 3 or n plus 3, we can say that the nth term is greater than or equal to n minus 3 over n plus 2 and less than or equal to n plus 3 over n plus 2. Now, since the ratio of the leading coefficients in the expression on the left is equal to 1, it's clear that the limit as n goes to infinity of that expression is equal to 1. And the expression on the right also has a limit of 1 as n goes to infinity. And since the terms of our sequence are trapped between those two expressions for all n, as n goes to infinity, its limit must also be 1. So the limit as n goes to infinity of n minus 3 times minus 1 to the n divided by n plus 2 is equal to 1. This type of limit calculation uses what's known as the squeeze theorem or pinching theorem. Suppose that for all n, the terms of the sequences a sub n, b sub n, and c sub n satisfy a sub n less than or equal to b sub n less than or equal to c sub n. If the limit as n goes to infinity of a sub n and the limit as n goes to infinity of c sub n are both equal to L, then the limit as n goes to infinity of b sub n is equal to L also. A remark. It isn't necessary that the inequality here be true for all n. We can reach the same conclusion if the inequality is true eventually. That is, if the inequality is true for all sufficiently large n. Here's an example of a type of sequence that we've studied before. Let f be a continuous function on the closed interval 0, 1, and let capital R sub n equal 1 over n times the sum as I goes from 1 to n of f of I divided by n for n equal to 1, 2, 3, and so on. Notice that R sub n is a Riemann sum of f corresponding to n rectangles, each with width 1 over n. And we've learned that the limit as n goes to infinity of this sequence is equal to the integral from 0 to 1 of f of x dx. Another example. Every irrational number is the limit of a sequence of rational numbers. For instance, one of the many sequences that converge to pi is 3, 3.1, 3.14, 3.141, and so forth, where the nth term is equal to pi truncated to n-1 decimal places. Also, irrational powers are defined in terms of limits of sequences. For instance, each value of the function f of x equal to x to the square root of 2 power is defined as the limit as n goes to infinity of x to the a sub n power, where a sub n is any sequence of rational numbers that converges to the square root of 2. Divergent sequences. A sequence that has a limit is called a convergent sequence. A sequence that is not convergent is called a divergent sequence. Examples. These are a few simple sequences that diverge. -1 to the n, as n goes from 0 to infinity, is the sequence 1, -1, 1, -1, and so on. Here's the graph of that sequence, which clearly has no limit and is therefore divergent. The sequence cosine of n pi over 3, as n goes from 0 to infinity, simply cycles through the values of cosine at multiples of pi over 3. Those numbers are 1, 1/2, -1/2, -1, -1/2, and 1/2, and the sequence consists of those 6 numbers repeated over and over again. And here's the graph of the sequence. The sequence 2n-1, as n goes from 1 to infinity, is the sequence of odd positive integers, 1, 3, 5, 7, and so on. And here's the graph of the first 100 terms of that sequence. Notice that this sequence diverges in a way that's fundamentally different than in the first two examples, in which the sequence cycled through a finite number of values over and over. Here, the values of the sequence are getting larger and larger, and therefore approach no limit. The sequence natural log of 1 over n, as n goes from 1 to infinity, is the sequence whose terms are 0, natural log of 1/2, natural log of 1/3, and so forth. Here's the graph of that sequence. All of the terms except the first one are negative, and they get larger and larger, therefore approaching no limit. An interesting divergent sequence can be defined by listing all of the rational numbers in the closed interval 0, 1. Let's do this by starting with 0, then 1, then 1/2, then 1/3 and 2/3, 1/4 and 3/4, then 1/5, 2/5, 3/5, and 4/5, and so on. Notice that for each successive denominator, we're simply listing all of the proper reduced fractions that have that denominator. Thus, every rational number between 0 and 1 is eventually in that sequence, and it appears only once. And here's the rather remarkable graph of that sequence. This shows the first 3,000 or so terms, which cover all the denominators up through 100. This sequence diverges in a way that's quite different from the previous examples. The terms do not cycle through any finite set of numbers, neither do they ever become greater than 1 or less than 0. Infinite limits. If the terms of a sequence a sub n eventually become and remain greater than every given number, we say that the sequence diverges to plus infinity and write limit as n goes to infinity of a sub n equals plus infinity, or simply infinity. For instance, here's the graph of the sequence a sub n equal to 3 minus cosine n times the square root of n. Notice that since cosine of n is less than or equal to 1, 3 minus cosine of n is always greater than or equal to 2. So the terms of this sequence are always greater than or equal to 2 times the square root of x. Now we know that 2 times the square root of x is eventually greater than any given number, and so the same is true for the sequence a sub n. Therefore, the limit of this sequence is equal to plus infinity. If the terms of a sequence a sub n eventually become and remain less than every given number, we say that the sequence diverges to minus infinity and write limit as n goes to infinity of a sub n equals minus infinity. Here's the graph of the sequence a sub n equal to log of 1 over n. For n greater than 1, a sub n is negative and gets larger and larger as n increases, eventually becoming less than any given number. Therefore, the limit as n goes to infinity of a sub n is equal to minus infinity. Here's the graph of the sequence a sub n equal to n squared times cosine n. Notice that this sequence has terms that are eventually greater than any given number, but it also has terms that are eventually less than any given number. Therefore, we cannot say that the limit equals plus infinity or minus infinity. We can only say that the sequence diverges. Properties of limits. Here we'll make the obligatory listing of properties of limits of sequences that are analogous to properties of limits of functions. These properties follow from a definition of the limit of a sequence that we have not discussed yet. We will give a precise definition of limit in the next lecture. Suppose that the limit of a sub n and the limit of b sub n exist. That is, the sequences a sub n and b sub n are convergent. The limit of the sequence whose nth term is a constant c times a sub n is equal to c times the limit of the sequence a sub n. That is, if all the terms of a sequence share a common constant factor, that factor may be brought outside of the limit. The limit of the sequences whose nth terms are a sub n plus b sub n and a sub n minus b sub n are equal to the limit of a sub n plus and minus the limit of b sub n, respectively. The limit of the sequence whose nth term is the product a sub n times b sub n is equal to the product of the limits of a sub n and b sub n. If the limit of b sub n is not 0, then the limit of the quotient a sub n divided by b sub n is equal to the quotient of the limits, the limit of a sub n divided by the limit of b sub n. If the limit of b sub n is 0 and the limit of a sub n is not 0, then the limit of the quotient a sub n over b sub n does not exist. If the limit of a sub n is equal to L, and f is a function that's continuous at L, then the limit as n goes to infinity of f of a sub n is equal to f of L. In other words, for a continuous function f, the limit of f of a sub n is equal to f of the limit of a sub n. Here's an example that describes an important use of this last property. If the limit of the natural log of b sub n is equal to L, then the limit of b sub n is equal to e to the L. To see how this relates to that last property, think of the natural log of b sub n as being the definition of a sub n. Then, b sub n is e raised to the a sub n power, so the limit of e to the a sub n is equal to e to the limit of a sub n. This is important because there are a number of interesting sequences for which it's easier to calculate the limit of the natural log of each term than to calculate the limit of the sequence directly. Some important limits. The limit as n goes to infinity of 1 over n to the pth power is equal to 0 for any positive p. This should be obvious because the denominator simply gets larger and larger as n increases while the numerator is always 1. Also notice that it's equivalent to the fact that the limit as n goes to infinity of n to a negative power will always be 0. The limit as n goes to infinity of x to the nth power is equal to 0 if the absolute value of x is less than 1, and the limit does not exist if the absolute value of x is greater than 1 or if x is equal to minus 1. This is about the fact that for any number strictly between minus 1 and 1, successive powers of that number get smaller and smaller in absolute value. For instance, successive powers of 1/2 or 1/2, 1/4, 1/8, 1/16, 1/32, and so on. Also, when x is greater than 1, we can say that the limit of x to the n is equal to plus infinity. But when x is less than or equal to minus 1, terms of the sequence alternate in sign, and so we can only say that the limit doesn't exist. The limit as n goes to infinity of x to the 1 over n power is equal to 1 for any x greater than 0. The terms of the sequence are successive nth roots of the fixed number x, which increase toward 1 if x is between 0 and 1, and decrease toward 1 if x is greater than 1. The limit as n goes to infinity of n to the 1 over n power is equal to 1. Note that the terms of the sequence here are 1, square root of 2, cube root of 3, fourth root of 4, and so on. Note that this limit is an infinity to the 0 power type indeterminate form, so it's not at all obvious that the limit should equal 1 here. Let's have a look at a proof. We'll take the limit as n goes to infinity of the natural log of n to the 1 over n power, because by a property of the natural log, we can bring the exponent 1 over n out front as a factor. So we have the limit as n goes to infinity of the natural log of n divided by n, which is now an infinity divided by infinity type indeterminate form, which we can calculate with L'Hopital's rule. Since L'Hopital's rule requires that we take derivatives of the numerator and denominator, we'll rewrite our limit as the limit as x goes to infinity of the continuous function natural log of x divided by x. Now we differentiate the numerator and denominator separately and obtain the limit as x approaches infinity of 1 over x divided by 1, and the limit as x approaches infinity of 1 over x is equal to 0. So the limit as n goes to infinity of the natural log of n to the 1 over n is equal to 0, which implies that the natural log of the limit as n goes to infinity of n to the 1 over n is equal to 0. And that tells us that the limit as n goes to infinity of n to the 1 over n is equal to e to the 0, which is 1. The limit as n goes to infinity of 1 plus x divided by n raised to the nth power is equal to e to the x for all x. Note that this limit is a 1 to the infinity type indeterminate form. Let's do a calculation to verify this limit. Since the index n appears in the exponent, we'll look at the limit as n goes to infinity of the natural log of 1 plus x over n to the nth power. That's equal to the limit as n goes to infinity of n times the natural log of 1 plus x over n, which is now an infinity times 0 type indeterminate form. And in order to use L'Hopital's rule, we'll rewrite the limit as a 0 over 0 indeterminate form and replace n with a continuous variable t. So we have the limit as t goes to infinity of the natural log of 1 plus x divided by t, all divided by 1 over t. Now we differentiate the numerator and denominator separately. The derivative of the numerator is 1 over 1 plus x over t times the derivative of x over t with respect to t, which is minus x over t squared. The derivative of the denominator with respect to t is minus 1 over t squared. Now notice that we have a minus 1 over t squared in the numerator and a minus 1 over t squared in the denominator, and so the expression here becomes x divided by 1 plus x over t. As t approaches infinity, the numerator approaches x, and the denominator approaches 1 plus 0, and so this limit is equal to x. So the limit of the natural log of our sequence is equal to x, which tells us that the natural log of the limit of the sequence is equal to x, which tells us that the limit of the sequence must be e to the x power. And finally, a couple of related limits. If x is equal to 1 in the previous limit, we have the limit as n goes to infinity of 1 plus 1 over n to the nth power equals e. This limit is often taken to be the definition of the number e. Also, 1 plus x over n is equal to n plus x over n, whose reciprocal is n divided by n plus x. So the limit of that reciprocal to the nth power must equal the reciprocal of e to the x. In other words, the limit as n goes to infinity of n over n plus x to the nth power is equal to e to the minus x. Growth rate comparisons. We can compare growth rates of sequences that diverge to plus infinity by looking at the limit of the quotient of those sequences. For example, the limit as n goes to infinity of the natural log of n divided by n to the pth power is equal to 0 for any p greater than 0. This means that the natural log of n grows much more slowly than any positive power of n. This is most interesting when p is very small. For instance, the limit as n goes to infinity of the natural log of n over the 100th root of n is equal to 0, even though the 100th root of n is very, very small until n is extremely large. But eventually, the 100th root of n becomes much, much greater than the natural log of n. The limit as n goes to infinity of n to the pth power divided by x to the n is equal to 0 for any p if the absolute value of x is greater than 1. This says that if the absolute value of x is greater than 1, then the absolute value of x to the nth power grows much, much faster than any power of n. For instance, a rather extreme case would be the limit as n goes to infinity of n to the 100th power divided by 1.01 to the nth power. N to the 100th power is much larger than 1.01 to the n until n becomes extremely large, but eventually 1.01 to the nth power becomes much greater than n to the 100th power. We note that the first of these two limits can be proved with one application of L'Hopital's rule. The second limit can be proved with repeated applications of L'Hopital's rule. The limit as n goes to infinity of x to the nth power divided by n factorial is equal to 0 for any x. So n factorial grows much faster eventually than the nth power of any given fixed number. For instance, an extreme case is the limit as n goes to infinity of 1000 to the nth power divided by n factorial. That limit is 0, even though 1000 to the n is much larger than n factorial until n becomes quite large. But eventually n factorial will become much larger than 1000 to the n. Let's look at a proof of this in the specific case where n is equal to 1000. Let's suppose that n is greater than 1001. Then 1000 to the n divided by n factorial is equal to 1000 times itself n times in the numerator divided by n times n minus 1 down to 1001 times 1000 times 999 and so on down to 3 times 2 times 1. Now let's pair off a 1000 from the numerator with each of the factors n minus 1 times n minus 2 and so on down to 1001 in the denominator. Each of those quotients is less than 1, so their product is less than 1. Now the number of factors in n factorial between n minus 1 and 1001 is n minus 1 minus 1000, or n minus 1001. So without the factors of 1000 in the numerator that we've paired off with n minus 1 through 1001 in the denominator, we're left with 1001 copies of 1000. So 1000 to the nth power divided by n factorial is less than 1000 to the 1001 power divided by n times 1000 factorial. Now 1000 to the 1001 divided by 1000 factorial is an extremely large number, but it's fixed and doesn't depend on n. So we have here a constant times 1 over n, and since 1 over n goes to 0 as n goes to infinity, this product approaches 0, and therefore 1000 to the nth power divided by n factorial must also approach 0. The limit as n goes to infinity of n factorial divided by n to the nth power is equal to 0. So n to the nth power grows much faster than even n factorial. This is actually easier to see than the previous limit. For instance, let's just look at 100 factorial divided by 100 to the 100th power. The numerator is 100 times 99 times 98 and so forth down to 3 times 2 times 1, while the denominator has exactly the same number of factors, and all those factors are 100s. The value of this quotient actually turns out to be about 10 to the minus 42 power. So it's easy to see that n factorial over n to the n is quite small even for moderate values of n. Finally, a few remarks about a type of notation that allows us to express these types of growth rate comparisons in a simple way. Let an and bn be positive sequences that diverge to plus infinity. We write capital O of a sub n less than capital O of b sub n if the limit as n goes to infinity of an divided by bn is equal to 0. In other words, big O of an is less than big O of bn if bn grows much faster than a sub n as n goes to infinity. This is the so-called big O notation for asymptotic order. Now let p, q, and x be numbers that are greater than 1. Then the first of the preceding limits says that big O of natural log of n is less than big O of n to any positive power, in particular less than big O of n to the 1 over q power, which is of course less than big O of n to the pth power, since 1 over q is less than 1 and p is greater than 1. The second limit above says that big O of n to the p is less than big O of x to the n. The third limit says that big O of x to the n is less than big O of n factorial. And the fourth limit says that big O of n factorial is less than big O of n to the n. So each successive sequence here grows much faster than the preceding one.